Okay, this is Unit 10B, Part 2, and we will be learning about power series today. So let's just jump right on in. So let's see what we have here. An infinite series, such as this one shown here, is called a series of constants. Each term of the series is a constant, as you can see. Now, an infinite series such as this sum n equal 1 to infinity, x minus 5 to the nth power divided by n factorial. And you can see each term, n equal to 1, n equal to 2, n equal to 3, and so forth. And here is your nth term, and this series is called a power series, and this series is centered at x equal to 5. So each one of the factors, x minus 5, is raised to the nth power. So each term of the series contains, there's your word, a power of x minus 5. So that is a power series. Let's define a power series centered at C. If x is a variable, then an infinite series of this form, there's a coefficient, a sub n, and there's a factor, x minus c, raised to the nth power. And you can see here n begins at 0 in this definition, n equal to 0 to infinity, but it can also begin at 1. We just have to watch that. And this is called a power series centered at C. And of course, C is a constant. Now, a power series in X can be viewed as a function of X, where the domain of F is the set of all X for which the power series converges. Okay? So we can view this power series as a function of x, where the domain of f is the set of all x for which the power series converges. So that's sort of our focus. We're wondering about the set of x values for which the power series converges. Now, one important thing to note is that every power series converges at its center, okay? So it may be the only place that a power series converges, but it always converges at its center. Let's go ahead and look at these three possibilities for a power series centered at C. The series could possibly only converge at C. A second possibility would be that there exists a real number, r, greater than 0, such that the series converges for x minus c less than r, and then diverges for x minus c greater than r. Of course, those are absolute values. So what is this here? You could look at it like this. Here is your center. We always converge at the center. Here is a distance, capital R, and so these would be your x values, x minus c, the absolute value. So that would be what we call the interval of convergence. Then you could have this last case where the series converges for all real numbers. So let's go through this again. Only at the center there is convergence. At the center and within an interval about the center, and all real numbers. The number r, this number r right here, is the radius of convergence of the power series, and that is something that is of interest to us. If the series only converges at the center, of course the radius of convergence is 0. If the series converges for all x, the radius of convergence is infinity. The set of all values of x for which the power series converges is what we call the interval of convergence, and that's right here. That's our interval of convergence. Okay? Okay, so one big note here. The ratio test is used to find the radius and interval of convergence. Why would we use the ratio test? Well, the ratio test says that a series will converge if this limit of a sub n plus 1 divided by a sub n, of course the absolute value is less than 1. So we will find this limit and then determine the values of x for which the limit is less than 1. Let's give it a try. Find the radius and the interval of convergence. I always call this R, and I call this IOC. You can also call this radius of convergence, but most of the time we just use an R. Be sure to check the endpoints. That is a big deal. What happens at the endpoints of the interval? Note, every time you are asked to find the interval of convergence, not the radius, but if you're asked to find the interval, you must check to see if the endpoints are included in the interval. Okay, so we are asked to find both the radius and the interval of convergence for this first series. So let's go ahead and find that n plus 1th term divided by the nth term. Okay, so we have a sub n plus 1 over a sub n, the absolute value, and that's equal to x minus 5 to the n plus 1 all over n plus 1 multiplied by 2 to the n plus 1th power. And then so when we take the absolute values, we lose this. The absolute values, we lose that, okay? Just to make note when you take the absolute values. Okay, now let's multiply. Since we would divide by the nth term, we'll multiply by the reciprocal. Okay. Now, I like to stack these n's, so we have n over n plus 1, and all of these are positive. We don't know if these are all positive terms. We'll keep those absolute values on there. And then we have x minus 5 divided by 2. Okay, and you could see that here by this 2 to the n plus 1. And the 2 to the n leaves a 2 in the denominator. And then, of course, your x minus 5 to the n plus 1 and your x minus 5 to the nth leaves an x minus 5 in the numerator. And then we just stack those n terms, okay? So now we'll go ahead and apply the ratio test. So we'll take the limit as n approaches infinity of the absolute value of n over n plus 1 times x minus 5 over 2. And that's equal to, of course, this limit is 1. And so this limit is just x minus 5 over 2. There's no n in there, okay? So this is just equal to, I can put it right here. That's just equal to the absolute value of x minus 5 over 2. Okay, so what does the ratio test say? The ratio test says the series will converge when the absolute value of x minus 5 all over 2, this right here, whatever comes out of that limit, is less than 1. Let's go ahead and work that out. The absolute value of x minus 5 is less than 2. Let's drop those absolute values. X minus 5 is between negative 2 and 2, and we have x is between 7 and 3, between 3 and 7, okay? So what do we have so far? We have so far, and I'll put it down here, our radius of convergence and our interval of convergence. What we know so far is that r is equal to 2. We know that for sure. The interval of convergence right now, we know that we have 3 and we have 7. We don't know whether these are brackets, one is a parenthesis, we don't know. So what I like to just go ahead and write is that right now, and we can always go to interval notation, is that 3 is less than x is less than 7. And if we have to make these less than or equal to, we will. So now what do we need to do? So this is finished. And I want to tell you, you can always find the radius of convergence at this simplified step. Okay? You can see that x minus 5 is less than 2. And this is always going to be your r once it is simplified like that. Okay? Okay. So do you also see that the center is 5? That's kind of cool. The center of that interval is 5. So I just wanted to show you that. Okay, and you can also see here that the center is equal to 5. Okay, we have to check endpoints because we're wondering, is this less than or equal to? Is this less than or equal to? So what do we have to check when x is 3 and when x is 7? So I'll go over right here and I'll just put check endpoints of interval of convergence. So the first thing we need to check is x equal to 3. That's that left endpoint. So what does our series become when x is equal to 3? Let's take a look. The series is n equal 1 to infinity. We still have a negative 1 to the n plus 1 power. And now when we put a 3 here, we have negative 2 to the nth power all over n2 to the n. N times 2 to the nth power. Okay? So let's go ahead and see if we can simplify that. That's equal to n equal 1 to infinity, and that's this negative, I write it right above this. This is actually negative 1 to the n multiplied by 2 to the n. Okay, that may take a minute for you to see that. Let me write this below. Trying to move all of that up. Just thank you for your patience. I'd like to just move that up a bit, and that's not working. Okay, so I do need to rewrite this, and let's just erase this and go right below it. Okay. So this is actually equal to n equal 1 to infinity. And now we have negative 1 to the 2n plus 1. And we have 2 to the n divided by n times 2 to the n. And as you notice, these will cancel. And we end up with n equal 1 to infinity. And we have negative 1 to the 2n plus 1 all over n. And that is just because this 2 is this square right here. Oops. Because we have that square right there, we are actually going to have n equal 1 to infinity, negative 1 over n. Okay? And let me write that right here. This is equal to negative 1 to the 2n multiplied by negative 1 to the first power. Okay? And this is a p-series. Okay, and that is divergent. And what would we write there? So if we have a divergent p-series, p is less than or equal to 1. Okay? Okay. Now, our other endpoint. So now since we're divergent, this definitely stays less than. Okay? Now we have to check when x is 7. X equal to 7. This is our other endpoint. And I was hoping I could move some of this over. I don't know if it'll work. Let me try one more time. It's not going to work. Let me try one more time. Maybe just moving this over might be a little helpful. There we go. Okay, now we have a little room for when x is equal to 7. So let's go ahead and plug 7 into our original series. And we have n equal 1 to infinity. And we have negative 1 to the n plus 1. And now note we have 2 to the n. So when we plug a 7 here, we have 2 to the n. All divided by n times 2 to the n. And as you can see, the 2 to the n's will cancel. And we end up with a negative 1 to the n plus 1 all over n. And this is an alternating series. This is also the alternating harmonic, but this is alternating series, and this is convergent. And of course, with the alternating series, if our terms are getting smaller than the previous one, and the limit is equal to 0, which it is, the limit of 1 over n, we could use that. This is also the alternating harmonic series, which converges. Okay? So now, what did we decide? We decided that our endpoint now does include a less than or equal to 7, since we will converge at x equal to 7. So we have our interval of convergence. You can also write it like this. And that's your interval of convergence. And here is your radius of convergence. Okay? Okay, a lot of work for just one problem. But again, we do have to check the endpoints. Let's go ahead and look at this next series. There's a lot going on in this next series. Let's go ahead and take a look at the n plus 1th term over the nth term, because that will give us an inequality for convergence. And we'll just take our time with this. Negative 1 to the n plus 1, x to the 2n plus 3. So you'll have to convince yourself that when you have a 2 and you put an n plus 1 in there, plus 1, you end up with 2n plus 2 plus 1, and that's how you end up with 2n plus 3. Okay, all divided by 2n plus 3 factorial multiplied by 2n plus 1 factorial, negative 1 to the n, x to the 2n plus 1. So quite a bit going on here. As you can see, these negative ones will go ahead and cancel out, and I will show you why. This is equal to negative 1 to the n times 1. So there's just a 1 remaining, whoops, when you cancel these two out, okay? So there's just a 1 in the numerator remaining, okay? And so what do you notice? We have an x squared remaining in the numerator. Convince yourself of that. I have 2n plus 3 in the numerator and 2n plus 1 in the denominator. So if you subtract those, you'll be left with 2, x squared. And then 2n plus 3 factorial is 2n plus 3 multiplied by 2n plus 2 multiplied by 2n plus 1 factorial, which would cancel there. Okay? So that's what we're left with. Okay? Now, if you note, this is always positive already, so now we can drop the absolute values when we go to take the limit. Okay? So we're going to apply the ratio test. And we're going to take the limit as n approaches infinity of x squared over 2n plus 3, 2n plus 2. Now, that is actually equal to 0. Be careful, because this x squared is not part of what n is approaching. N is approaching infinity, not x. So maybe I can get this. Let me try to just get that highlight off of that. There you go. So it's just n that's approaching infinity. So that is equal to 0. And since that's equal to 0 and 0 is less than 1, therefore the series converges for all x values. Why is that? Because any x value you have here won't change this limit of 0. Okay? So how do we write that? Our interval of convergence is negative infinity to infinity, and our radius of convergence and you could write it like that, is equal to infinity. Okay? So it's that ratio test that gives us that result or that inequality that helps us with convergence. Let's try one more before we conclude this second part. Okay? I would like to know what the n plus 1th term divided by the nth term is so that I can apply the ratio test. And that's going to be n plus 1 factorial multiplied by x minus 3 to the n plus 1. And we can have a true division problem here and not multiply by the reciprocal. That turned out very nice. So we end up with the absolute value, and n plus 1 factorial divided by n is n plus 1. And then we have 1x minus 3 term remaining. Now, I want to show you something. N plus 1 doesn't need absolute values on it, but the absolute value of x minus 3 does, okay? Because n is going from 1 to infinity. So that's pretty important here, okay? So let's apply the ratio test. And we're going to take the limit as n approaches infinity of n plus 1 multiplied by the absolute value of x minus 3. And that's actually equal to, remember, n is going to infinity. But this is the deal. This is actually equal to infinity, except if x is equal to 3. Because if x is equal to 3, then we would have 0 for this term, okay? So how would we write that? We only converge at the center. You can see that this is the center of this power series, and we will converge only at its center. So the interval of convergence is none, and the radius of convergence is 0. So this series converges or only converges at its center. Okay, and that concludes